Today we will talk a little bit about mathematical models or mathematical models for systems. As we mentioned before in previous videos, control systems is basically the essence of control system is the development of mathematical modeling. For the majority of the systems models that we will call them in a general form later during the video, already are set. That means that already it was a study behind that and how this mathematical models represent the behavior of a system. So we will start with the definition of mathematical modeling or mathematical model. Okay, so mathematical model of a system is a replica of the relationships between the input, right, and the output or outputs. Okay, well, the actual relationship that exists between the input and the output of a system have been replaced by mathematical expression, right, as we know from mathematical background. For example, consider a motor has a system. Well, the input to the motor is a voltage, right? It's a motor. The input of the motor is a voltage. Okay, and the output is the speed of rotation, right? In this case is angular velocity of the shaft, right? For many systems there is a apparent linear relationship between the input and the output. So this means that the output is proportional to the input. And if the input is double, the output is double. And this remind me when I used to make the example of when we produce soda, for example, right? So if we produce 10 liters of soda, right? So because of this one is representation from the input. So that means whatever input is here, it need to be a proportional representation of the output. If the input is multiplied by some constant, then the output is multiplied by the same constant or by the same multiplier, right? It also means that if input 1 produce output 1 and input 2 produce output 2, then an input equal to the sum of inputs, let's say 1 and 2, will produce an output equal to the sum of outputs 1 and 2. And here is related to if you have feedstock and you have several inputs, right? The output need to be equivalent to the input in size. Thus, if there is a linear relationship between the output and the input for the motor that we were talking about, then the mathematical model is that W, that is the output, right, is equal to GV. where in this case G is the constant of proportionality. That means a proportional or gain that equate the direct relationships, but in proportionality means, right? So this relationship implies that if the voltage is changed, then should be an immediate corresponding change in the shaft speed of rotation. Well, this will not be the case since the motor will take some time for the shaft to get up to the new speed. So the relationship is thus just the relationship between the voltage and the speed. When the system has time to settle down to any change in the input, it refers to what are called the steady state conditions. Thus, to make this clear, we could rewrite the equation, right, has a steady state value of the rotation steady state value of the rotation equal to the gain multiplied for the steady state value of the voltage. Okay, so if you will see here, the proportionality exists only if the time has been passed and the conditions are settled on in order to have a proportionality. So if G is a constant of proportionality, so is the proportion constant to change due to the settled down conditions that has been reproduced by the continuous system or system in operation, right? In order to have a continuous output or a desired value that is the end goal in control systems. Okay, so if we would like to rewrite again that one, so G is equal to a steady state of the rotation or the value of W over a steady state of voltage. Okay, so the constant is called here a transfer function or gain of the system. This one we call it is the famous transfer function or gain of the system. Okay, in general, we can define the transfer function as the ratio of the steady state output to the steady state input, right, for a system or subsystem. So in this case, so a steady state output over a steady state input, and this is how we will represent from now a transfer function. When we were describing for example in a block diagram, if our system is composed with a couple or more block diagrams, right, we can extract the transfer function from the first block and the next one and the next one and the next one. So we will have several transfer functions, right? So now here is a technique that we use that we collect algebra of blocks. So when we have a series of blocks, okay, like for example you that currently are you drawing your process flow diagram, so you will have block 1, block 2 and block 3, Okay, so if we do that, we will have a transfer function here, 1, transfer function 2, and transfer function 3, right? But in control systems, because remember, when we are designing a control system, it's better to work with a block diagram itself. So when we have that one, we use algebra or block diagrams algebra, and it works exactly like exactly how we manage algebra in maths to reduce the blocks in order to simplify, right, the system or transfer function that we are looking at, right? So, for example, when we have this system in series, not in parallel, so what we do is that transfer function multiply transfer function 2 and transfer function 3, and later at the end of the day you have an overall transfer function, right, that represent the mathematical representation of the system that include, in this case, 3 block diagrams, right, in order to control the overall input versus the overall output. Okay, and this is how we go about. Just to wrap up, mathematical models are based on the techniques. Actually, we can classify it as a mathematical models for open loop systems. Mathematical models for open loop systems. Yes. And mathematical models for closed loop systems, sorry. Okay. And we know the difference if, like, for example, in thermodynamics, when we it's an open system, of course, it's open in this way, has a open, and when it's closed, that means related to control systems. So we have the process here, right? But we have a closed loop. Okay, so where we have here we have the transfer function from the system, and later here we have the transfer function for the measurement device, that this can be the sensor that is giving the feedback to we call it set point, that it can add it or subtract signals in order to compensate, right? So the next action will be modify the input in order to have the desired output. Okay, and of course the combination of mathematical models, it can carry you for mathematical models for multi-element closed loop system. And multi-element means that you are working with several diagrams, right, with feedback. It can be a measurement transfer function feedback in order to compensate an action to have the desired output. So this is the introduction to mathematical models for the class instrumentation and process control. Next class we will talking about the different models that we can expect to find during our professional exercise. And as we know, we'll focus more a little bit in chemical processes, basically, for example, chemical reactors and so on, because include more basics or include more variables to consider in order to exercise or to start the design of control systems. Okay, so see you next time.